After that introduction to the goal for one of the biggest goals for Calc 2, we want to get started right away. How does one make this bridge between the two? And there actually is several ways of doing this. Today we're going to look at some very cute ways of establishing some of these bridges, and this should be enough to get us excited about it, I think. And then later on we're going to learn a more general method, meaning that the things we learned today are super cute and amazing, but their power is limited. They only work on some functions. Some of these crazy functions we will be able to find their corresponding bridge, but some other ones our method won't work here. And so think about this as just the first dose of bridgeness. Okay, so we'll start off with a little bit of review from basic algebra classes. And so in basic algebra classes you would have had a polynomial like this, where you go through all the different powers of x, the 0th power, the first power, the second power, the third power, and on and on and on, different powers of x in consecutive order. And it turns out that that's actually really easy to add. I'll explain real quickly how one can go through the argument. You could say, okay, you remember in regular algebra class, if you have x plus 1, that could be factored into x minus 1 times x plus 1, right? And similarly, if you have x to the third minus 1, that could be factored into x minus 1 times x squared plus x plus 1, and so on and so forth. Well, the trouble is a lot of people don't go through this so on and so forth, but if we were to do it, x to the fourth minus 1 would be equal to x minus 1 times x to the third plus x squared plus x plus 1. Now to add these, we're going to take a look at this last line here. We're going to focus on the last part here and see, imagine that you could solve for that piece. Solve for it, meaning that you isolate that piece, meaning that you get rid of this piece. To get rid of this piece, you would have to divide it and place it on the other side. So from here, you could say that x to the fourth minus 1 divided by x minus 1 is equal to x to the third plus x squared plus x plus 1. And it's customary to write this in the different order, starting with the 0th power. So you could say x to the fourth minus 1 all over x minus 1 is equal to 1 plus x squared plus x to the third. And using a pattern here, or if you can use some sort of proof by induction, you can see that you could easily do it for other powers. The key thing to note here is that whatever power you end up here, 3, what you do is you put the next one up on top. That would be 3 plus 1 would be, the next one would be 4. The fourth power over here, and then the bottom is just x minus 1. So for example, if I wanted to do x to the 10th minus 1, I already know how that would go. If I divided by x minus 1, that would be 1 plus x squared all the way to x to the 9th. That's how you add this geometric series. This is adding all the different powers of x to the 0, x to the 1, x to the 2, all the powers of x in a very, very elegant way. So having said that, then this becomes easy. If I wanted to add up all the powers of x, starting with the 0th power all the way to the 50th power, that would give us x to the 51 minus 1 all over x minus 1. Right, and that's a simple way of showing how to add. These sums are famous, how to add geometric sums. The sum of geometric sum is so, the series, a geometric series is so easy to compute. You just go one higher than that, and minus 1 all over x minus 1. You could put this to the test using something super basic. For example, you could go 1 plus 3 squared plus 3 to the third. That should be equal to 3 to the fourth minus 1 all over 3 minus 1. If you add that correctly, that should be equal to 81 minus 1 all over 2. Okay. So, by the way, this is 26. Look at it. This gives you 80 divided by 2. That gives you 40. 40 should be the same thing as 27 plus 9 plus 3 plus 1. Okay. Pretty neat, right? All right, so so this could be added this way because of the geometric sum. Same thing if you were going to go all the way to 75. That would just be, since this is 75, you take one more, that puts you at 76, and then you do the rest of it like that. That gives you the geometric sum. You do this all day long, but it becomes really, really interesting when you take it not to the 70th, but to the infinite power. If you have infinite power, that becomes x to the infinity plus 1 all over, or minus 1 all over x minus 1. And this, of course, becomes x to the infinity. Since, for example, infinity plus 1 is equal to infinity. Okay, and then something interesting happens here. What if the absolute value of x was less than 1? What if? Try to imagine what would happen here if the absolute value of x was less than 1, for example, like 0.9. If you take that number, 0.9 here, 0.9 times raised to the infinity power, 0.9 times raised to the infinity power plus 1, that would give you 0. So this piece would vanish, and all you would have left is negative 1 all over, well, you'd have a 0 if you want, all over x minus 1, or said differently, negative 1 over x minus 1, or said even differently, 1 over 1 minus x. Okay. This tells you, what does it tell you? It tells you something amazing. This tells you that for if your x's are less than negative 1 in absolute value, then the sum of all the powers of x is equal to that. And just pause for a second. This means that if I, for example, take any number less than, where the absolute value of that is less than 1, say x is equal to 0.5 or half, then 1 plus a half squared plus a half to the third plus a half to the fourth, and on and on and on, all the way to infinity, infinite many times. That's going to give me negative 1 all over 1 half minus 1, which would be negative 1 over negative 1 half, which is equal to 2. Amazing. If this is telling you, for example, that if you were to add all powers of 1 half, starting with a 0th power, first power, second, and you went all the way to infinity, you would get exactly 2. 1 plus a half plus a quarter plus an eighth, etc. All that is equal to 2. Amazing. You can make a picture of it like this. Here's 0, here's 1, here's 2. This is 1. This would be, that number right there would be 1 plus a half. That number right there would be 1 plus a half plus a fourth. Okay. And that number right there, 1 plus a half plus a fourth plus an eighth, and so on and so forth. The more you keep adding this piece and that piece and that piece and that piece, you always add half the distance to the 2 and half the distance to the 2. Eventually, if you keep doing that forever and ever and ever, that's going to be infinitely close to 2. Okay, or we say that the limit of the partial sum sequence goes to 2. That'd be the fancy way to say it. Anyways, this in fact gives us the first look into this bridge. On the left hand side, we have this bridge 1 over 1 minus x. That's not a polynomial. On the right hand side, we have 1 plus x squared plus x to the third. That actually is a polynomial if you allow yourself to have infinitely long polynomials. And so we found this very, very first bridge. In fact, these two are exactly equal. And this is very, very much not a polynomial. And this is an infinitely long polynomial, infinite degree polynomial. And they are exactly the same, so long as we restrict x's a little bit. And there you go. Our first example of this bridge between two functions.